Okay, I'll get going now if everyone is in, I guess. My name is Charlie Gracie. I work for IBM on their runtime technology for about 13 years now. I'm going to be talking today about OpenJ9, Eclipse's new Java VM. So it's a new project we've just open sourced at the Eclipse Foundation. I'm a committer on this project, and I'm also the project lead for the Eclipse OMR project, which is a smaller technology subset of our VM that I'll talk about later that's consumed by OpenJ9. Sorry. So some important disclaimers. Don't use any of this information to make any of your product decisions based on what I say. Skip on to the next slide. So OpenJ9. OpenJ9 was created in September 2017 this year. It was announced early in the month. We're an Eclipse project, and the interesting part is we actually are dual license. We're Eclipse public license version 2. We were actually one of the first projects to switch over to the new license, and we're also dual license as Apache version 2.0. The links are there. Go check out our project if you like, and all contributions, questions, comments, feel free to use GitHub issues and let us know everything that you see about the project. So to actually get the VM, I'll talk a bit in a few minutes about how you could actually go compile it yourself. But to actually get binaries to use to start off, if you just wanted to get up and going quickly, there's this great project called Adopt OpenJDK. It's actually run by the London user group, and their goal is to actually provide binaries, a standard location to go get OpenJDK binaries. So as soon as we open sourced our OpenJ9, they actually started creating OpenJDK builds with OpenJ9 and providing them as well. So you can go download them there. Our 4 platforms that are currently available on there are easy to go download. Okay, so if you wanted to build OpenJDK with J9, if you've ever built OpenJDK, it's actually a very similar process. You have to go get the main repo, invoke a script to go download the rest of the sources, configure and compile, and your JDK is ready. This one is an example for doing Linux x86. If you were doing Linux PPC or Linux 390 or AIX, it's very similar. You'd figure out the path differences pretty quickly. The main thing here is I keep saying OpenJDK, and I'm talking about our OpenJ9 project. Why do I keep saying OpenJDK? That's because OpenJ9 is actually just the virtual machine part itself. It's not actually all of the class libraries. We still rely on all of the class library portions. And if you've seen this picture from a JDK 8, there are lots of projects and different components of the JVM. So really what we've actually provided is just sort of the core runtime itself and a few of the extra classes and different areas where they actually are very tied to the VM implementation. So in this picture, all of the boxes are very straight edge. They look very well confined, but actually in reality, a bunch of these components actually have interdependencies. So to provide this type of information, we have to go and provide a bit of extra changes to the OpenJDK libraries themselves, or the code itself. 3 clicks every time, I guess. So really the VM has connections everywhere across the JDK itself. It's more like an octopus reaching into everywhere and sticking on. So when we actually tried to tease it out to just be our VM, there were a lot of extra changes. But we're really focused on just the core part and how that ties into the JDK itself. So we have this other project that you would have to go if you want to download, which I talked about in the first line. That's where the git clone was happening. This actually is the OpenJDK code base itself, taken directly from the Mercurial code base, uploaded to our GitHub, and applied any of our changes that we need to do there. That's not hosted as an Eclipse project, just due to licensing and that types of stuff, because that's a GPL code for the most part. And this on a daily basis is actually all the changes happening in OpenJDK are actually mirrored in here, so it's always up to date, or regularly up to date. So another thing I sort of mentioned a bit earlier was the Eclipse OpenJ9 project also consumes an OMR project. So this slide here is really showing you Eclipse OpenJ9 and all of the sort of technologies and where those technologies are being used / envisioned to hopefully be used in the future. So you can see that for under the OpenJava runtimes, there's OpenJDK with Hotspot, and then you have the OpenJDK with OpenJ9, which is also consuming the OMR project. The IBM SDK on the right-hand side is basically showing that 100% of the code that we're using in our open source projects is being consumed on a daily basis back into our product line. This is not another piece of code we've just open sourced and let go off into the community. This is actually being actively developed. I'd have to look at the numbers again, but we've had hundreds of pull requests developed by our team, and a few external people already contributed in the last month and a bit. So that's where 100% of our active development is happening. To the left of the OpenJava runtimes is sort of the OMR project. So the OMR project, we created this in 2016 to really build this extensible and reusable piece of virtual machine technology. We really believed that our GC, our just-in-time compiler, a bunch of our other parts of the runtime didn't really have to be only used for a Java runtime. They could actually be consumed in other runtimes. So like a GC really collects objects. If you tell it what your root set is, it could be used in any runtime. It doesn't actually matter the particular runtime. So we've actually gone and extrapolated these parts of our components out and made that available so other runtimes could pick them up and use them if they'd like to. Like I said, it was done in March 2016 was the first initial release. That's the links for it. It has the same licenses that the OpenJ9 project has. And I believe this project was actually the first one to switch to the EPL v2. And the OpenJ9 was second. So we're all here to hear about OpenJ9, how it works. So now I'm going to actually sort of lift the hood off the car, and we're going to dig in a bit into the VM itself. I'm going to focus on different parts that I actually believe are interesting to Java developers, in particular in the Eclipse ecosystem, doing different, working inside the Eclipse itself, or building plugins, or doing a bunch of their technologies. So I'll call out some of the particularly things I think are interesting there, explain how that technology works, and how I think it will benefit people that are working in those types of environments. So if we start out with the world's simplest Hello World program, called a Hello Service to change it up a little bit for everybody. So everybody has seen this simple program. I don't want to have to put that on the screen every time, so I'll talk about executing it through a jar file. So that's basically the compiled version in a jar so that we can run it. And if we run it, we get this output. Everybody's seen this, how it works. Even the most junior developers probably run this in 5 languages. But what I want to do now today is actually go in and talk about the different parts of OpenJ9 and how that actually runs and how you end up with the output and a bunch of the different components involved. So what's the JVM actually doing when we run that command? The first thing it does is it actually loads a lot of classes. It loads your class, so we would actually go load the Hello service, but it's all of the classes. That depends on all of the things that it uses and a lot of different classes that are actually required to bring the JVM up itself to start up. So how many classes is it actually to start up a simple Hello World? If you put the verbose class command line option on, you can see pages scroll by. I didn't actually do the W count here on the lines, but it was way too many pages to actually display everything. So I put a few classes in here just to sort of show the type of output that you would see when running, including your class. But this goes on for pages and pages. So with that being one of the things that's happening during the startup of your application, if you can actually do something to improve the number of classes, the size it takes, or the speed at which you can create those and load them, that would actually help possibly your footprint in startup. So one of the key sort of values that our team has always had, and sort of the heritage from our VM comes from a Smalltalk VM originally, then onto Java ME VMs. So we've always been really focused on footprint, but while keeping as much performance as we can. So our sort of real idea is that if you choose the right data structures, the algorithms that you use to work on those kind of just write themselves. You need to really pick the right data structures. And there's a great quote here from Rob Pike, that data structures and not algorithms are actually central to programming. So for class loading, the structure of a Java class file is actually defined as part of the JVM spec. Don't need to go through all of this. It's not particularly that important. But the key parts here are if you wanted to load a class, a lot of the things you would need to do if you were just using the class files directly themselves, if you just say read that into memory and used it, is the layout isn't particularly efficient. There would be a lot of searching through a bunch of these arrays, through the method array and those types of things, to actually find the data and to be able to use it efficiently. So one of the big things we've done is we've created the J9 ROM class. And I'll talk later about RAM class. We've divided class file sort of into two parts. But the ROM class, we believe, is a better class file implementation. So when we go, it keeps all of the same type of details from the class file, but it removes a lot of variability in size and in complexity so that we can improve a bunch of stuff at runtime while keeping it still having all the information that is in the class file that's static. So to create these ROM classes, there's links at the bottom here. People can go look through the code if they want. It's some interesting code in the ROM class builder. A class file will go from the class file. We have to still do all the static verification that's required by the JVM spec, or that we should do from the JVM spec. Goes through a ROM class builder, and then you get out this ROM class. The interesting part about a ROM class is that it's actually could be burned in ROM. This actually came from our ME days. It actually is position independent, and nothing gets changed as you're going through it. So it's not all of the class, but it's the position independent, non-changing part. So again, another structure definition. The only reason I put this one up here is so you can see it's kind of similar in the names, but it's the J9 SRP values that are everywhere for types. It's the interesting one. In the class file, a lot of these were embedded arrays or pointers to other data to other locations. We said this is position independent, so everything that the ROM class talks about can only reference other data that's relative to the current location in that structure. So if you wanted to fetch the superclass name, that would actually just be an offset of, say, like 50 from the top of your structure, from the location of that field. So you always take field plus offset, and that's actually your location. By doing this, that means that we actually have this data that never has to be transformed, and it's the same for every class. No matter, sorry, not same for every class. A version of a class that you have, so class foo, if you loaded that in 10 VMs, the ROM class is exactly the same between all of them, regardless if even you changed any of the class hierarchy. So now I've just said that all of this stuff doesn't change. You could burn it in ROM. The way Java actually calls methods means we'd have to go look everything up all the time, and that's probably actually slower than the class file itself. So what we do is from our ROM file, we actually create a RAM file. So the RAM class is actually the live representation of the class in your VM at any one time. Two VMs running the same class could have different RAM classes. They could be slightly different if you happen to change the class hierarchy or something, but the ROM class would always be the same. One of the interesting things is from these two ROM and RAM class pair, we can actually always go recreate an equivalent class file. It's not the same class file, but it is equivalent. And we need to be able to do that for things like class transformation. So RAM class, again, very similar structure to the ROM class, but this one is up here because it actually now has real pointers. This is live data from your actual running VM. And it's used sort of to cache a lot of the things that you would do in lookup, for method lookup and those types of things. So once you've resolved a method in Java, if you want to go execute that, you know where it is. You don't have to look it up. It would be in the resolved methods part of the J9 class. You only have to go as far as there to look it up. So with this distinction of RAM versus ROM classes, why am I spending so much time in my 30-minute talk talking about this? It's because of this feature we call shared classes. What this is in this example you have 3 JVMs. If they're all running the same app or a similar app, you would have your VM, and then the white one is representing RAM classes, the black boxes are representing ROM classes. Every time you go to load any of these, so creating the RAM class and the ROM class, there's creation time, there's memory usage, and those types of things. Those are all costs. But I said the ROM classes across any VM doing the same class would be identical. So what we do is we actually have we can use this memory mapped area, and you actually only get 1 copy of it if you're using shared classes. So that would then actually reduce your footprint, and also it improves your startup time, because you don't have to go convert these into ROM classes all of the time. You actually just go you're just using memory mapping the file, and away you go. Again, that's why it has to be position independent, because it gets loaded into memory wherever it happens to be for that new process. The footprint improvements can actually be up to 20% on a lot of applications of your memory used to start up the VM. So at the point when you start to run, you could have actually saved up to 20% of your footprint up to that point. So I went in through that part. That's one of the features that we actually have that I believe a lot of people could use. If you're actually doing plugin development, or you're like me and working on 8 things at once, so I have 8 Eclipse workspaces open, that is one area where you can actually get some improvement. And on the plugin development, every time you start it up, you just get quicker turnaround on being able to actually do your development. So how does this actually end up looking for my Java code? Because I'm trying to give everyone a good overview of how everything works in our VM. So we have across the bottom our ROM and RAM classes. Those are all actually still represented on heap as a Java Lang class, as a Java Lang class loader. These all have the appropriate pointers back and forth so we can find them. But I just wanted to quickly show there is all of the actual Java side of the world here as well for these things, and not just all under the covers native memory for everybody. Okay, so I've talked about class loading. Now we want to actually go, how does my code actually get executed on the system? So if you think about it, in all of your applications, really your thread is the execution context. So I want to look about how we execute your program on our different threads and talk about sort of the structures in our VM. So our VM, as the J9 Java VM, is this sort of main structure for everything. We avoid all kinds of statics and such things so that we can actually, you could in theory have multiple VMs all attached to one another and still executing. In practice, that's not happening right now, but it is something and the goals we try and keep around. Every Java Lang thread that you have on your heap, we have a J9 VM thread underneath the covers, and then again there's an OMR VM, an OMR thread from the OMR project, which is really just mapping this to an OS thread for you. So that's how you do all the communication actually with the OS. So how does your application now execute in the VM? So every J9 VM thread actually maintains an interpreter instance itself. So we talk about having one J9 VM, but really every thread itself has an instance of the interpreter. And that's so that it can keep track of all of its own state, and we can actually have them easily go off and run at the same time parallel to one another. So the main things that the thread has to keep track of to be able to do this is which method you're executing. From the method, it can find out your bytecodes. At any time, the current PC is pointing at your current bytecode you're executing, and we have a Java stack. In the J9 VM, the Java stack and our C stack are actually completely separate, and that allows us to grow or shrink the Java stack as we need to, just by relocating some objects. And I say shrink, in practice it only ever grows. So the JVM thread itself is actually keeping these SPA0, which is the start of your arguments, PC and method. But we actually, to be performant, we actually don't keep those up to date all the time. They're only actually updated when we know that something is going to use them that's not yourself. We have a very cooperative threading model in J9. So if the GC, say, wanted to go do a garbage collection, we actually ask all of the threads to stop, and once they have, then we go off. So that would be a point where they would actually copy these from the machine registers back into the VM structure itself so that we could perform the GC. So the interpreter that we have per thread, interesting fact, used to be written in assembly code that was generated from Smalltalk. Comes from our Smalltalk VM days. That's what we knew. That's how we generated the assembly. But that's a very high bar of entry for anyone new to the team to go learn Smalltalk, learn our language that's written on top of Smalltalk to generate things. And there's no way we could ever open source that. So at about Java 7 timeframe, we actually went and rewrote the interpreter in C++. That did come with a hit to performance on startup a little bit, but we've since recovered that, and meant we now have to actually keep some inline assembly around, handwritten inline assembly that we use for every platform. But now it's easy for everyone to look at. There's some code from the bytecodes on the side there. I think everyone here, regardless of what languages you know, could actually read that and understand and make some simple changes. Push, pop, they're pretty straightforward. This executes the bytecodes, and it also allows us to do something we call INLs. So instead of actually calling a Java native for everything, that's really slow, a JNI native, for ones that we know about that aren't going to do anything, like because it's our native, we can actually not do a lot of the cooperative things that you should do for JNI natives to make it faster. So these INLs are just sort of system class library natives that can run quickly without having to pay a lot of the overhead for JNI. If anyone does a lot of work with JNI, it can be very slow calling that in and out all the time. And it also handles transitions to the JIT. The garbage collector technology, the garbage collection technology that we have in OpenJ9, you'll see a lot of similar terminologies to all other runtimes. It's got a very highly parallel and scalable generational collector. That's our default collector. If you wanted to pick it on the command line, it's called GenCon. We also support a region-based large heap GC, very similar to G1 in the OpenJDK builds. But one of sort of the key parts to a lot of our GCs is that we actually really favor using less memory where possible. So in a lot of other runtimes, you say you could use up to 2 gigs, 4 gigs of memory on your system. Pretty quickly, you'll be using 2 or 4 gigs of RAM on your system. If shrinking your heap doesn't result in any noticeable performance loss, we favor being really small and using a smaller footprint. So we grow less aggressively on heap growth, and we also contract way more aggressively than a lot of the other collectors and VMs out there, which then reduces your footprint again. And in a lot of cases, another 20, 40% smaller footprint can be seen just by switching over to our VM and due to heap sizes, with still keeping similar performance. We have a world-class just-in-time compiler technology. This technology's heritage actually comes from being shared with the IBM static compilers. So it's a very well-designed and has had lots of 20 years, I think, of being developed. So it's very capable. The just-in-time compiler, everyone thinks of just a code generator. It's really more in the fact that it actually does a lot of profile management. It actually does a lot of computes a lot of runtime assumptions, and actually has to be able to do this in a very efficient way. So it's got a very high-performing runtime collection system built in. In the OpenJ9 JIT, it actually has multiple tiers of compilations. So not every method needs to be compiled at have the same amount of optimizations applied. And mostly, the main reason for that is you don't want to put everything through your 500 optimizations if it's only used a little bit of the time. So we sort of do this staged and adaptive compilation where the methods will be recompiled at a higher level if they still continue to be something that needs more optimization. And some of these transitions actually generate code that actually profiles when you execute it. So for a short period of time, one of your methods would actually track all of the different ways that you branch throughout the code during execution and things so that the JIT can actually recompile and make sure those paths are actually all in line together. For the JIT, if you want to see which methods are compiled, there's another command line option, and you can see it'll output, and then when it recompiles, if it does so, you'd see on the same method again with just the other op level. But the cool part of the JIT is for years now we've actually supported AOT in our shared classes cache. So AOT is actually ahead of time compiled JIT code. So this actually allows you at startup to, again, memory map in, basically ready to run JIT code for your application. So in our shared classes cache, the first time you run, it would keep a bunch of information and compile some code stored in the cache. And then every time you run afterwards and use the same cache, that code will be executed on startup. Just because the method's in that cache, it still takes part in all the regular JITting after the fact. So it's just to get you up and going a bit faster sort of way. So again, this one can be anywhere on 10 to 30% of your startup time improvements just by enabling shared classes on your command line. So again, lots of workspaces or doing plugin development can really save a lot of time in your day. So when we first put our code out there was some decent community reaction, so a bunch of tweets. The interesting ones are sort of near the bottom because we've been talking about how much our memory footprint savings are, but then we actually had other people go and compare directly to OpenJDK, and even Doug compared us to a Node.js application, and using OpenJ9 with Vertex, the similar application written in Node was actually using less memory on Java than it was in Node. So sort of the old, everyone saying that Node is smaller, using it in the cloud and those types of things. There's some examples here where you can actually write stuff in Java using Vertex that's actually faster, or sorry, actually smaller footprint. I don't want to make claims about performance. And then again, we've had a few other people just go and execute things and talk about being like 40, 50% of the footprint requirements of OpenJDK with similar performance, or OpenJDK with hotspot. So how can you get involved if you want? You can go download it at OpenJDK, adopt OpenJDK. They're all there. Come visit us at GitHub. Try it out. I've made claims that it'll help. It'll improve your workflow under Eclipse or doing whatever development you're doing. Let me know if I'm wrong. Point out problems. Tell us when there's successes. But we'd like any and all feedback. We're an Eclipse project, so completely open governance like any other project at Eclipse. So come out, contribute, become a committer. Even better. So that's it for me. Does anybody have any questions?
Do you know if anyone is working on macOS co-op, headless, so not the UI part of macOS?
Like OS X, so we'd run on OS X? Yes. It's being worked on by 1 or 2 people internally in their spare time, and just because it's an open source project, they're just playing around. And I believe there's 2 external people also looking at it as well, and getting a bunch of it up and going.
Part of the product, right? But does anybody agree this with OpenJ9 then?
As OpenJ9 as the project, nobody would be running the TCKs. IBM consuming it back as part of the IBM product, we'll be using it and still providing a fully certified JVM based off of OpenJ9.
Okay, that would be okay.
Yeah.
Right. Why are shared classes not named by default?
That's a good question. We keep talking about it. Why isn't shared classes enabled by default? Since it's a win, or sorry, why it's not? It's a good question. We keep going back and forth on it. And really it comes down to it's actually this other memory map file that's staying persistent on your system. So we don't want to be going and creating this persistent file for people when they don't expect it to be there. And if you don't know it's there, it's very easy to have scripts going and cleaning things up behind, like cleaning up all of your runtime directory. So you probably, in those cases, you wouldn't get wins anyway. So we want it to be an opt-in thing. We just try and talk about it very loudly so that everyone knows about it and does it. That's not saying it won't become more of a default thing as we go forward. And if anybody has any input, like that type of stuff, that could help make it become something that it is on by default. Back there.
It was clear that once this JVM from IBM was presented in the context of cloud computing, and there was, as far as I remember, a statement that in a multi-tenancy environment, if you pick up a VM for a second tenant, the goal or the memory footprint that is targeted is 10 kilobytes, which would be impressive for Java, definitely. So what would be the footprint in having such a scenario in JVM 9?
So you wouldn't see that type of wins in just a vanilla VM. So if people were here talking about multi-tenancy, it was probably about a beta that we had for Java 7 or 8, I believe, where we actually had a bunch of other multi-tenancy work in the VM for doing that. For this, right now, if you run 2 VMs, whatever your heap size is that you're consuming, you're going to at least have that much heap again. But a lot of the rest of the stuff now via the shared classes catch, if you're using it, is actually shared. So in those scenarios, if you're bringing something up, let's say you're doing small work, you have a 4 meg heap or an 8 meg heap, you're probably going to get by with a couple of megs. I don't actually have the real numbers plus the heap size, but that's something that we can look into and should talk about on the website.
Would be good to know what would be the improvement compared to, maybe not compared, but what would be the tech for J9?
Definitely, I'll get something we'll get looking at and get up there. Yep. So again, somebody externally actually, is looking at getting it up and going on ARM right now. There's been again, I know it would compile there and work there. It's just a matter of getting it going now in the new build environment and getting all of that stuff out there. But it is something that is being looked at by a few external people as well. Don't have dates or times when it will be available.
Is there any plans to bundle the OpenJ9 VM with Eclipse installations? Because sometimes people confuse VMs and have multiple installed, or the wrong ones installed, or whatever.
It hasn't been anything we've talked about at this point, but it could be bundled with it, I guess. It's not something that I'm aware of that people have talked about.
What's the list of GC elements? Was there one there that is going to be great for server throughput where you want to have no downtime or no?
The default one's probably, for a lot of workloads, the best in that area. There is also balance, so if you have really large heaps and you're trying to keep your GC pods at a minimum, that one usually does a bit better. But we also have the metronome GC collector, which was our soft real-time collector. There's a trade-off for throughput versus responsiveness. You can get 3 millisecond max pause times in the soft real-time GC for a trade-off on performance. By default, you're only going to get, I believe, 70% of your utilization is given to the application. The other 30% is to the GC at just wall time. And then there's other things about it that are actually our trade-offs so that we can do the GC in small increments to keep the pauses under there. But yeah, there's different levels here depending on how you want to trade off your application performance versus your pause times. In the back? Yep. I'll have them on SlideShare 5 minutes after the talk probably. And you?
Yeah, just a comment to bundling. I know there
something that needs to be investigated, and we have to make sure that it does work properly for everyone.
And so, yeah. In most things we measure, it's very competitive. Again, I'll point a bunch of actual documentation. I'll put them up and tweet it afterwards after my slides and stuff are up. I'll get some links from people. We tend to actually scale on very large systems much better. But nobody's really running on 512-way machines with a single JVM these days, so I'm not sure that is a huge benefit anymore, but we do tend to scale on that really large machines a bit better. Usually about 10–15% less GC time of the total GC time, not of your runtime. So you're talking about switching from 2% down to 1-point-something% of your runtime, not huge runtime wins. The just-in-time compiler, all of the benchmarks that are getting published, it's leapfrog with all of the JVMs all of the time. At the current state, I'd have to go look at them, but there's definitely benchmarks where OpenJ9 is faster, and there's also going to be benchmarks where Hotspot's faster. It kind of just depends on your workload. Okay. Okay. Yeah. Okay, cool. I'll actually just share that again as well too. Yep. There was a Java 1 presentation from this year, and I believe there was some performance numbers in there. So I'll share that as well. I'll retweet that again for anybody who hasn't seen it. You? A Docker image with the VM already compiled and ready to go. I know people have been looking into it. We provide a Docker image that I don't think it has a compile right now, just as a build environment for people to make it easier to build. But I'd have to look to see the current state. I don't believe we do. You? Interesting question. I don't have the answer. Yep. This is a Java 9 VM. In the name of the very first, I should just jump back, I guess. This one, the project has JDK 9 at the end. If there was a JDK 8 one, it would be there with a JDK 8 as well. I know people have also sort of looked at that as well. Thanks everyone for attending.